So let me introduce CIRC, that's Czech Institute of Informatics, Robotics, and Cybernetics of the Czech Technical University in Prague. The Czech Technical University in Prague is quite old university, is the second oldest technical university in Europe, established 1707, and it's currently the leading technical university in the country, consists of 8 faculties and 5 institutes. And CIRC, Czech Institute, is the youngest one. It has been established 9 years ago. And since the very beginning, we concentrated our efforts to interdisciplinary research in artificial intelligence with the focus to applied research in Industry 4.0, energy distribution, smart cities, and healthcare. So we were able to construct quite a new building, which accommodates today more than 250 researchers and 100 PhD students. And we opened it in May 2017. Today, it's full of research staff inside. Since the very beginning, we concentrated our efforts towards building a center of research excellence, linking research excellence with applicability and applications of results. So we would like to perform in the whole string from excellent research towards applied results in industry. And we are building an AI ecosystem for manufacturing. That's the third AI ecosystem. You are getting information about it today because Prague considers to be an ecosystem. Brno is considered to be an AI ecosystem. And now our institute is also organized as an AI ecosystem with the focus to manufacturing, smart cities, energy distribution, healthcare, and so on. The number of researchers you can see, I mentioned it already. And as a matter of fact, we have very small governmental institutional funding. So 97% of our funding comes from European projects, national projects, and industrial contracts. It's approximately equal. That means 1/3 from EU projects, 1/3 from national projects, and 1/3 from industrial contracts. The budget of the institute has been 15 million euros last year. And we can document that we are really doing excellent research by the fact that CIRC contributed to a very high evaluation of AI research at the Czech Technical University. Czech Technical University has been recognized in June of this year as number 4 in computer vision and number 8 in robotics in Europe. That means in 9 years, we passed through a very long trajectory towards excellence. We are strongly networked internationally. We participate in 4 of 6 EU centers of excellence in AI, and it also documents the level of excellence of our research. The core research facility, which is quite unique, is the test bed for Industry 4.0. That's a set of machines, robots, algorithms, tools, which enable to build an experimental production line on request and to test control algorithms, to test, let's say, cooperation of human and robotic teams, simply to prepare the production line in a research facility. So that's quite important part of our activities. Testbed is supported by the flagship RICAI project. RICAI means Research and Innovation Center for Advanced Industrial Production. That's the largest project of the teaming program of EU. And as a matter of fact, there are 4 founding partners: CIRC, Technical University in Brno, its Institute CEITEC, DFKI Saarbrücken as the largest German Center for Artificial Intelligence, and ZEMA Saarbrücken, which is also a good partner for DFKI for testing. Since this year, there are 2 additional partners, Fraunhofer Institute in Dresden and Technical University in Ostrava. So that's flagship project. I'll talk about it a little bit later in more detail. We are the seat of National Center of Competence, Cybernetics and AI, which supports mainly collaborative research between academia and industry. We are the seat of the National Center for Industry 4.0, responsible for know-how transfer and contracted research. We participate in large European project EU EIT manufacturing with 50 partners and funding, quite important funding for us each year. And we are also serving as European Digital Innovation Hub for AI. We are seat of the Central European Office of CLARE. That's the most important European organization bringing together research labs and experts in the field of AI. We are seat of the Central European ELIS office. That's a similar organization focused at machine learning. We are seat of Gaia-X and IDSA organizations. So we are trying to build an AI system for academia, industry, cooperation, and know-how transfer, combining diverse forms of project funding, combining different groups of experts, starting from engineer, PhD in cybernetics, control engineering, up to medical science and energy distribution. So we are building such an ecosystem. You can see there are plenty of companies and institutions which participate in the National Competence Center for contracted research and for know-how transfer. Many of them are small and medium companies. This is very important for local industry to receive the latest results in the field of AI and in the field of software systems for manufacturing from local academia. And we also have plenty of partners in the National Center for Industry 4.0. So you can see again plenty of small and medium companies. The main industrial partners are Škoda, part of Volkswagen concern, Siemens, and T-Mobile. I'm going back to Research and Innovation Center for Advanced Industrial Production. As a matter of fact, in each of the locations, in each of our 6 partners today, there is a smaller or bigger test bed. And the goal is to link these test beds to, in the future, to prepare and develop experimentally production line in a geographically distributed way, being linked by 5G communication and virtual and augmented reality. So the goal is to have a couple of robots here, a couple of robots, for instance, in Saarbrücken, to link the parts of the production line using 5G internet and virtual and augmented reality, and to force such production line to operate like being in one place physically. This will speed up the processes of ramp up of production in the future, will eliminate the need to transport physically robots and heavy equipment between different labs. So it's a cost-saving solution. And as a matter of fact, after 6 years of operation, we should establish a non-profit organization which should manage and operate system of testbeds in Europe using this technology without any need to buy the equipment once more or to physically transport it. So currently, we are nearly completing the testbed. That's a state-of-the-art experimental environment for distributed production. And we are making a lot of R&D tasks and projects using this equipment. We are engaged in innovation processes. And of course, there are students and PhD students everywhere. That means it's a very important tool and platform for education. Concerning the technology, we have currently a reconfigurable assembly line with 6 robotic stations, more than 30 other robots mainly robots which operate in the mode of human-machine cooperation. We have flexible conveying systems, machining robots, heavy robots for specific types of machining, hybrid additive and subtractive manufacturing tools, 3D printers, automatic warehouse, robotic vision lab, and also fully furnished 5G station, first in the university environment in the Czech Republic. As a matter of fact, in this test bed, we have organized together with the US partners, especially with experts from University of Berkeley, University of Pennsylvania, University of Cincinnati, workshop on intelligent manufacturing, and that was quite successful event, which enables us to extend our cooperation, not to operate just with European, but also US partners. Our test bed has got, as a matter of fact, 4 parts. Part 1, robotics and flexible production. There are tens of lightweight robots for human-machine cooperation. Part 2, which is in the basement, because this part consists of production machines, very heavy production machines, for instance, exploring laser technology, machines which are able to add and subtract material on the same in the same space, and so on. Then we have 3D printing center, which is located separately from security reasons, and smart grid lab, which uses our photovoltaic plant on the roof. You have to understand that in this phase of Industry 4.0, energy saving is one of the important optimization tasks. And as a matter of fact, we made advertisement for Industry 4.0 production. But today the companies which are fully furnished with robots suffer from the prices and strongly rising prices of energy. So we need also to try to find a solution how to reduce their energy costs. Here are some pictures from our test bed for Industry 4.0 located in our facility. We have partners in Germany, in ZEMA in Saarbrücken. There is a Power for Production, Cyber Physical Production Systems lab, which can be easily linked with us, and we can perform jointly geographically distributed experiments. The same is true for Smart Factory Living Industry 4.0 demonstration facility, which is located in Kaiserslautern. I would like to mention also some selected results, because we orient our efforts to industrial applications. So, for instance, the researchers in Recade were able to enhance the efficiency of pressing processes at Škoda Auto is the exploration of virtual reality. We have quite successful application at Airbus. There are already 3 assembling lines in Hamburg and Hanover equipped with the production scheduling system, which reduced the assembling processes by 10 to 15%. We speeded up the production lines, and Lego, and as a result, Lego factory or Lego company extended their presence in the Czech Republic by adding new production lines. We participated in the process of integration of 5 robots in the welding cell. The robots were from different vendors, built by different vendors, and it was necessary to build a neutral interface. And as a matter of fact, we can document 15% of energy saving in this robot integration task. We developed anti-COVID half mask, prepared it for manufacturing in an SME within 6 days. At the very beginning of the COVID pandemic, so in 1 week, we have had a solution which was then distributed free of charge, and everybody with specific types of 3D printing machines was able to print this half mask, high quality half mask by its own equipment. As a matter of fact, we know about tens of thousands of masks which were printed out in this way. Overall progress of our institute and especially of our applications in cooperation with industry. Škoda Auto, Siemens and T-Mobile are the key partners. Tens of local SMEs are absorbing our solutions, and we are currently tightly cooperating with DFKI and with Professor Wallster in defining new second stage of Industry 4.0 strategy. And we have jointly identified 5 hot topics. Explainable AI solutions for cooperation in hybrid robot-human teams, because the people should understand what the robot intends and vice versa. Integration of machine learning methods by using semantics. Current machine learning methods usually use just neural nets. We would like to use more complex models, which are structural models, and we call them big models, to integrate the smaller solutions. 5G communication on the factory floor. Zero error production, that's very challenging topic because we would like to reduce the costs of errors detected which appear, which do happen during the manufacturing processes as soon as possible. That means we are checking and verifying the result of each step of production and standardization. We jointly defined with Germany a large project AI-QAMA, which has already been funded by BMBF, and we are waiting for funding. BMBF is German Ministry for Research, and we are waiting for funding from Czech side. So future steps. Our strategy is to build the research around the testbed for Industry 4.0 and to get funding from large-scale projects like European Large Research Infrastructure Program, like Test and Experimental Facility Program of EU. We were successful in this, and 1 month ago we were awarded by 8 million euros to run testbed as test and experimental facility for European research space. And we are preparing even bigger project. IPCEI means important project of common European interest, which is called Comenius. I'll talk about it in 2-3 minutes. So we are bringing together experts in AI, robotics, mathematics, medicine, architecture, transportation, and social sciences. And we orient our efforts from basic AI research up to applications, creating flexible teams. So this is a quite nice prototype of AI research ecosystem. Concerning the future project, which we have submitted 2 weeks ago, and which is called, which is part of the European Cloud and Edge Continuum, we prepared a project which supports system integration industry. What's the main idea? You know, we are developing specific solutions for small and medium companies. This solution is developed, is used in one small plant, and this is it. We would like to reuse massively the data, experience, solutions from this experimental work, and to offer the solution to many others, maybe to extend it, maybe to use their data, their private data, sensitive data for testing. So we would like to link R&D application field, that means Czech Institute, to bring all the data we use for development of specific solutions into industrial cloud. And then, and there are 2 companies which will take care about it, and then reuse it, building a specific type of industry above the industrial computational cloud. That means industry which consists of many small and medium companies able to grasp the already achieved solution, to use the data which are collected by different vendors, and to prepare new, maybe much more complex or efficient solutions for the others. So that's the idea. We are building a specific data center or hierarchically organized data space with the center in Opatovice, which is being built under the auspices of T-Mobile. We will use specific IoT platform and Certicon orchestration platform to optimize the data and algorithm flow, because each flow of data, each flow of algorithms requires a lot of energy, and we should consider energy as being a very important component. And of course, we will use CIRC as research facility and Far Edge Comenia Lighthouse as a center for small and medium companies, which will leverage the space prepared by T-Mobile, in which operate two platforms, IoT platform Comenia and Certicon orchestration platform. The center should be near the city of Hradec Králové. Near edge cloud facilities should be in Brno and Praha, and far edge facilities in regional cities. So it will be hierarchical network, which will enable small and medium companies to ask for solutions and to ask another small and medium companies which create a system integration industry for help and for delivering solutions. So all these projects should cost 481 million euros in 7 years, and we are addressing really the market needs of our region. We will offer the solution to the whole Europe. There is support from other partners, from other projects of the same type, like Open Reference Edge Cloud Infra, which is of the similar size, Common Secure Edge Cloud, and sustainability from energy efficiency. So that's the future. We think that our institute is on the right track. We can serve as a quite particular example of efficient EU networking and cooperation. We can document our contribution to industry, including SMEs, and to the society in EU. The key role in building of this center played DFKI and Professor Wolfgang Walster as the godfather of Industry 4.0 in person. And our importance, or let's say quality of results, was highlighted by the visit of the German Bundespräsident, Mr. Frank-Walter Steinmeier, last year. This year we were visited by German Vice Chancellor, Mr. Robert Habeck, and Vice Chairman of the European Commission, Mr. Franz Timmermans. All the visits were motivated by the guests. That means they asked for the opportunity to visit our facility and to see how such a center can look like. CIRC is an open institution, so we are linking excellence with application of results. We are ready to receive and educate students, postgraduate students, postdocs from any country around the globe. We are ready to cooperate in joint research projects. We are ready to provide expertise or solutions to industrial bodies, from startup up to large companies. And we are ready to share our testbed facility using 5G communication, fast internet with any other lab in Europe, Japan, US, Turkey, everywhere. And we are deeply interested in cooperation with Turkey in AI and also in other fields. So you can find the information on our website. So there's very brief information about our institute. Thank you very much for your attention. And now I think it's time to give the floor to Professor Zdeněk Hanzálek, who leads our Industrial Informatics Lab, and he will present his research of his team in the field of autonomous vehicles. So Zdeněk, it's your turn.
Okay, do you hear me?
Yes, we can hear you.
Okay, All right,
Can you
so,
please make it full screen?
okay, do you hear me well?
Yeah, we can hear you, but we also need a full screen presentation.
Yeah, like this. Is it better?
Yeah, that's better.
Okay,
And
so,
also, I'm sorry for interruption, but can you please a little bit move your camera so we can see your face better? Yeah, so thank you.
okay. So, ladies and gentlemen, welcome. So I will speak today about automated cars, and in particular, I will mention two use cases that we have developed in the past. One of them is related to scale down model of automated car, which is like competition between universities that are using the same hardware, and they compete in let's say F1 fashion. And the second use case is related to real car and some test software that we have developed for steering and driving the car in slalom use case. Okay, so first of all, maybe it would be better if I will show a small video here. I hope you see something. So I will go to some interesting place. So here you see, for example, the competition which was held in Prague like 1 year ago. So you have two types of competitions. One is head-to-head racing that is shown here on this video. And another one is the competition which is shown here when the formula runs alone around the lap and we measure just the fastest lap, right? So the hardware of the equipment is the same, including NVIDIA TX board, so that it becomes a really, let's say, fight of ideas, fight of algorithms, and you cannot just buy, let's say, better solution. Okay, so this is the first use case. And the second use case is shown here. So we have got from our colleagues in Porsche Engineering Services in Prague, Panamera car. We have connected our electronic control units via vector boxes to FlexRay bus of the car in order to be able to steer automatically and to accelerate and brake automatically. And then the objective was to run automatically through the row of cones. The cones can be dispersed or they can be in line. And so the objective is to detect the cones in a picture, to measure their distance by lidar, and then to plan trajectory and steer the car and follow that trajectory, right? So it's to be, the aim is to replace the testing drivers so that the tests are easily reproducible. Okay, so that's about my videos. And now let me go to the presentation back here. So a little bit about how it is done inside. So we have, as I said, let me move a little bit Zoom stuff here so that I can read it. So you have a bunch of universities that take part in this F1 10th competition. It's organized mostly by University of Pennsylvania, and once or twice a year there is like physical competition related to some robotic conference, so to say, mostly. Okay. So the teams have the same equipment, as I said, and they are supposed to develop the different algorithms. University of Pennsylvania has nice educational material on how to assemble lidar, electronic boards, and mechanical stuff, so that you can relatively quickly get such experimental platform, right? And then the objective is to develop your algorithm, right? So you need to process data from LiDAR, from camera, localize the model. You probably want to also go around and track how the lab is done, what's the form of it. So you need to do some mapping as well. And then once you have a map, and once you know your position, you can plan trajectory and to keep formula on that trajectory, right? Another possibility is that you do it just in a reactive way, that you go through unknown lab, and you just detect the space where you should move, right? That's also a possible way of doing that. So our solution that we are developing currently now is based on optimization. We divide lab into segments, and then we use kind of homomorphic transformation of unit square into the segment, and then by genetic algorithm we suggest some waypoints in the segment, and we simulate car planning through those segments, and then through those waypoints, sorry, and through all segments, and then we obtain value of criterion function, and we can compare that value with other chromosomes that have used different waypoints. Okay, so that's one possible solution. Or you can use, for example, MPC or whatever you want, right? So these are, for example, some recordings of the experiments where we have also put some obstacles on the lab so that the task is a bit more difficult. So the blue stuff is our reactive algorithm, which is called follow the gap. The green stuff is follow the gap enhanced a little bit with information about the map. And the red stuff is the genetic algorithm. Okay, so and now let me speak a little bit about the second use case, which is the slalom with Panamera car. So we have very similar equipment to the first one. So we have again LiDAR camera, and here in addition we have a differential GPS. And then furthermore, we are connected by FlexRay to car buses, and therefore we know all sensor values that we might be interested in, for example, odometry of wheels, and we have the same hardware equipment, which is NVIDIA TX2 with robot operating system, as middleware and libraries to be used for development. So the task is relatively straightforward. You detect the cones by camera, you do data fusion between camera and LiDAR, therefore you can measure the distance of cones as well, and you do a trajectory planning, excuse me, and trajectory following. So the task seems to be simple, but in practice it is not so simple. For example, imagine that you use a classical camera with fisheye effect. So you need to do undistortion of the image. Then as you see, cones are relatively small in the picture. So you don't have so many pixels representing the cones. So you don't see even the most distant cones that are maybe several or maybe 100 meters distant. And you have also troubles with LiDAR, which doesn't work well when the road is wet due to the physical principle of laser detection. Then we have had many troubles with differential GPS. Sometimes the signal is lost, so you have to do like a Kalman filter, which fuses odometry from the car and your, let's say, history of move and your current position obtained by the GPS. and many more. So many practical problems occur when you do practical experiments. As far as for the structure of the solution, so here you have input sensors. On the bottom, you have actuators for steering and accelerating. So you process the image from camera, you detect the cones, and then you fuse information from little camera to know real cone position because you measure the distance by lidar. Then you use also Kalman filter to know your own position and heading. And once you know the map of cones and you know your own position and heading, you can plan trajectory, and then you can keep the car on that trajectory, okay? Of course, there are always some imprecisions. For example, we have been able to position the cones with precision of several decimeters, which was finally sufficient for our experiment. But it's not so easy to see all these parameters when you start the experiment. You don't have all these pieces of the puzzle in place. So here very briefly, so you localize the let's say potential cones in the figure. Then you use histogram of gradient as a feature descriptor. Then you use the SVM classifier to distinguish cones from non-cones using supervised machine learning. This is a figure which shows difficulties with differential GPS. Sometimes signal is lost. And since you have just 1 point, and for heading, you need to have at least 2 points. Then at the beginning, you don't know heading of the car, but once the car starts to move by Kalman filter, you obtain heading as well. And for trajectory planning, we used so-called bicycle model, which is a very simple description of car kinematics. And we used this bicycle model to plan trajectory while offering, let's say, one waypoint beside of each cone. The strategy is different for the cones that are in the middle of the row and for the cones that are at the end of the row, because the maneuver has to be different at the end. And then once we have these waypoints, we use the local planner, which is a classical optimization problem, which drives the car on different position and heading to another different position and heading, right? So these are like simulation experiments that you can see here with cones in line using symmetric U-turns, cones in line with asymmetric U-turns, which seem to be more efficient, and finally dispersed cones. Okay, so you have seen some experiments on the videos that I have shown. I will just mention some experiences we learned. So it's quite a holistic experiment because it includes a lot of know-how from perception, data fusion, planning, optimization, control, car interfacing, and so on. So there are many function blocks that may create some troubles in real experiments, and experiment itself, it's like a logistic exercise. If you forget something, then experiment is lost and you have another trial like in 2 weeks, for example. Then also, if you are missing some of the blocks, then you cannot undertake experiments, or you cannot learn whether precision of other boxes is already sufficient. So it's very good to start early outdoor experiments as soon as possible, so that you may have maybe less functional solution, but a solution which already reveals weaknesses of other functional boxes, and you can improve them rather than making all of the boxes perfect, and then assembling them with ease and doing everything on site. That's nearly impossible. You have to go in iterations and start to improve your solution and to mitigate bottlenecks and so on. Okay, so thank you very much for your attention, and I give the token to Peter, if I'm right. Huh?
Hello. So I will start the sharing of my screen. And let's start. So hello, I would like to first introduce myself. My name is Petr Marek, and today I should say you something about the experiments we do at Czech Institute of Informatics, Robotics and Cybernetics around conversational AI. So I'm working in the team called Alquist, and we are developing a conversational social bot with the same name, Alquist. And our team has been competing in the Alexa Prize competition for several years already, and it's annual competition for students' team, and their goal is to develop a conversational artificial intelligence. And the overall goal is to have a conversation that is coherent and engaging about popular topics. So you can imagine movies or sports or science, for example, and the conversation should be 20 minutes long, ideally. And everybody in the US can say, Alexa, let's chat. And it starts the conversation with one of the competing social bots. And after the conversation, the user provides rating on a 5-star scale. And the best 5 teams proceed to the finals, where 3 interactors and 3 judges have a conversation with the best social bots, and they decide who is the winner. And our team has been quite successful in this conversation, in this competition, because we started in the year 2017 and we were on the 2nd place. Then in the 2nd year of Alexa Prize, we were able to end on the 2nd place again. 3rd year, it wasn't so successful for us because we ended on the 3rd place. But recently, last year, we were able to win this competition, and we beat it top US universities like Carnegie Mellon or Stanford. And at least according to the Amazon, Alquist is the best social bot in the world. And today, I would like to show you some problems that we faced and how we solved them in the development of our social bot. So the first key thing is that, yes, we are developing AI, but the whole design of the social bot is not just about the AI algorithms. Because imagine this, you are working really hard, you are improving your AI algorithms, the precision, you are improving your intent recognition or entity recognition models, you are working on multiple screens. And I would like to show you a hypothetical graph of the performance of like your AI, if I simplify it. So in the beginning, the improvements are really easy. So your performance is increasing pretty rapidly. But then you reach some kind of like spot where the performance starts to flatten because each improvement is really hard. But you are still trying to do. And now I will show you like the hypothetical graph of user satisfaction. So yes, in the beginning, the user satisfaction, like the number of stars that you obtain, is slowly increasing because your AI algorithms are really bad and they are making a lot of mistakes, and you are improving it, so the rating is also improving. But then it stays kind of like flat, and yeah, and it's not improving that much. And why is that? Well, the reason is because the users usually don't care about the like precision or any AI metric. They want to talk about their favorite movies or music or about politics. They want to feel that the social bot can surprise them or that they are cared of. And so like improvement of 5% is not very visible to the users. But still, I would like to show you a few examples of abilities that we identified the social bot needs to take care of and how we approach this problem. So this will be like more practical presentation. So first, I would like to show you like how we solve the ability to say something. So how do we do it? Well, we represent each conversation as this dialog tree. So each conversation is represented as some graph where each node represents either what the bot says or what the user says. And I want to imagine that you want to design some initial conversation. So first you want to think what should be the initial message of the social bot. So it can be, for example, the question, who do I have a pleasure speaking with? And then you have to come up with some possible answers. For example, some users can say, my name is, and the name. And then you have to think about the response of the social bot to this input. So for example, the social bot can also greet the user. But on the other hand, other users can just say hi or nice to meet you. And then you have to also think about the possible response and so on and so on. And in this way, you basically can kind of conversation. Where is the AI? The AI is in the branching points. And we use algorithm called intent recognition, which is a text classification algorithm, and it decides where the conversation should proceed when real user has some input. And this is kind of rule-based, so it's not that much AI as we can do better. So what we've been using, there was a large research of generative models and large language models. For example, you may know GPT-2 or GPT-3, and we can use these large language models to generate the responses almost on the fly. But we have to be smart because we've been experimenting with this approach already. We used Dialog GPT, and this was the responses that we obtained. The problem is that these language models are usually trained on, for example, Reddit, and Reddit is not particularly known for pleasant conversations. So some of the responses can be pretty offensive. So you have to filter the responses pretty well, or you have to fine-tune your models. So what are the key area of research in these large language models or neural generators for our team? So it's control, because we want to control the style or the content of the generated response. We also want to provide additional knowledge into the models, so the models are able to talk, for example, about actual topics or recent topics. And we also want to improve the efficiency of these algorithms because they are kind of data hungry and resource hungry. So we would like to decrease the hardware requirements, so we would be able to run them much easier. So this is the ability to say something. But what happens when the users say something unexpected? Because when we design this rich tree, we can come up only with limited amount of responses that the users can have. But they can say, for example, what is the population of Brazil, or they want to talk about their visit with the sister. And we should be also able to handle these inputs that are in the unexpected way. So this program has two steps. First, we have to recognize that the input is unexpected. And in the second step, we need to come up with some response. So how do we recognize that the input is unexpected? So we use universal sentence encoder, which converts the input and the examples from the dialog tree into vector representation. And then we calculate the cosine similarity of these resulting vectors. And if the similarity is above the threshold, then we know that this is something expected, so we can do the intent recognition. But if it is below the threshold, we know that this is unexpected input, and we should handle it differently. So next we do a classification whether the input is question or not. If it is question, then we do question answering. And if it isn't a question, we use generative model. So for the question answering, we used Amazon Eevee, which is their question answering system. And it is kind of like a black box, so there's nothing I can say about it. But in the case of generative model, we use model that is called the Dialog GPT, and we feed into it the context of the dialogue, basically the history of what has been said. And then the Dialog GPT generates several candidate responses, and then we use the second model, which is called Dialog RPT, which is a ranking model, which selects the best response to say to the user. It was trained also on the Reddit, and the signal is upvotes, width of the conversation, and also the depth of the conversation. And we found out that the first model that is like on the rating of the response performs the best. So we also fine-tuned the model on different data sets, and we found out that it really makes the difference. So we use empathetic dialogues, which is a data set of nice dialogues. So now we know how to say something. We have the ability to recognize and generate responses to unexpected inputs. So the last part, very important part, is to make the dialogue engaging. So imagine that there is a user and he wants to talk about Matrix, the movie Matrix. So how can we make the conversation for him interesting? We found out that we can get some fun facts. It is a short trivia from a Reddit, and we can present it to the user. So for example, we can say that Keanu Reeves was trained for the Matrix for 4 months in karate for the Matrix. But then we have to incorporate it into the conversation, because if this is all the Socialbot says, then the user don't know how to proceed. They can probably say something like, okay, because there is no question for them to like continue in the conversation. So we can use something like, did you know that? This like template question, and it works for some time. But if we say like multiple fun facts in a row and each is followed by, did you know that? It kind of is repetitive and the user satisfaction starts to decrease. So if we can come up with some different method that can generate a question that is more contextual, that would be great. And we found out that, yes, we can again use the generative model, the Dialog GPT, that takes the context, that takes fun fact as a context and generate a question that is somehow related to the fun fact. But the problem is that we want to generate just questions. And these models are trained on any data or any text, so statements as well as questions. So first, we had to modify the model in a way that it takes a context and also a control tag that says, now we want to generate a statement and now we want to generate a question. So we can switch it. So it works kind of like a switch that we can turn to generate just a question. And then if we use it, then we can generate question for all the fun facts we need. And what are the results of these experiments? We found out that our model is able to generate the correct dialogue act. It is either question or statement in 90% of the cases on an average. So now we have like a lot of abilities for our Socialbot. We are able to say something, we are able to recognize something unexpected, and we are able to react to it. And we also know how to make the conversation engaging by incorporating fun facts and by generating a question by generative model, for example, the Dialog GPT, which is based on GPT-2 model. So this was just a few examples of problems that we are working on here in Czech Institute of Informatics, Robotics, and Cybernetics in Prague. And also I have a news that our team was again selected to compete in the Alexa Prize 5, in the Alexa Prize Grand Challenge number 5. So we will be working on these problems in the following months again. So these are some contacts if you would like to learn more, we have also nice promo videos that you can find on our YouTube channel. So definitely check that out. And that's from me. So thank you.
Thank you. And it was a great overview to learn about Czech Technical University, CIRC, forgot the last letter. And also I want to underline the things that you have mentioned, like creating an AI ecosystem that includes different partners and also cooperation, because without cooperation, even you are the strongest team, it won't be enough to reach out the goals that you are doing right now. And it's a great job. Thank you for sharing. And it was great to hear from both the success stories and also the structure that you have done. And I hope this will encourage both collaboration between Turkish and Czech AI ecosystems. And if you have any other comments before we are moving to the next session.
So may I say a couple of words? You mentioned that cooperation is quite important, and we feel international cooperation is quite important from the point of technical achievements, because people from different backgrounds, from different countries can bring new culture into research. And it's very important for, let's say, also mutual understanding in political aspects. So I think collaboration is something what we do prefer. And I would like to repeat that our institute is open to Turkish students, postdocs, and that we would like to see any kind of projects running together, industrial projects, maybe EU-funded projects. We are very open, and each such initiative will be welcome. We will try also to initialize some project or exchange of students from our side in the near future. Thank you very much for the opportunity to present Czech Technical University, and especially CIRC as the youngest institute of the Czech Technical University, to Turkish, let's say, community of AI. And I hope we will meet Turkish colleagues on different conferences or bilateral meetings in the near future. Thank you very much for this opportunity.
Yes, thank you. And thank you, Mr. Marek and Hanzalek and Marek. And it was great, as I said. And also it's important to hear about the private sector and university collaborations. And generally, most of the good practices, best practices are coming from this kind of collaboration.